Let's start with where we stopped last time. Last time we discussed about database approach in general, where we start with this definition of the terms database, information and the knowledge. And then we discuss about how to extract this raw data from real world entities, or in other words, what mean by raw data, that is the characteristic of real world entities. And then the information is the process data, and knowledge is the minimum information required to identify entities. Then we also discuss about the need of database management. Then we move to the to discuss two type of data management techniques. The one is the manual and the other one is the automated database management. And then under the automated management, then we discuss that all these data need to be stored in persistent storage, or in other words, the secondary storage. And then we talk about the how data can be stored on secondary storage or digital media, and that's where we talk about these disk characteristics. Data can be stored on magnetic storage, but in the magnetic storage, the advantage is the high capacity, but whereas in terms of the access mechanisms, only sequential access is facilitated. On the other hand, the other storage media like disk, compact disk like DVD like things, they facilitate both sequential and the random access. That is the advantage, but obviously in terms of the capacity, somewhat lower than the magnetic tapes. But that's why we talk about we discuss about the memory hierarchy, and the memory hierarchy means the organization of different electronic storage media into a particular order depending on the access speed or the capacity. And generally, when the capacity is high, access speed is low, and when the capacity is low, access speed is high. That is the general feature of this electronic storage media. And in the storing data on this disk, and we discuss this disk architecture. There we mainly look at the hard disk like things, and in this disks are manufactured so that the single disk has multiple platters arranged into a cylinder architecture. That means the set of disks put in one above the other to form a cylinder like thing, and that those disks are fixed into a disk arm, and then disk can be rotated. And in addition to that, in order to transfer data from disk surface, there is a disk head on top of each surface, and which is fixed to a disk arm. This arm can move from forward and backward direction, but this can be rotated in clockwise or anti-clockwise direction. And if a disk usually every disk has two surfaces, but if we can store data on both surfaces, then we say doubly spaced disk or the platter. If only one surface is used for the data storage, then single spaced platter. And each surface of this disk is also organized into a collection of tracks. So that is basically track mean the circle, and then those tracks for each and every surface in the disk, a parallel track is there. And if we can see 10 tracks on the topmost surface, 10 parallel tracks are there on each and every surface of the disk. And then because of that reason, for a given disk, number of tracks is equivalent to the number of cylinders. Number of cylinders. A cylinder is a collection of parallel tracks. And in addition to that, each track is partitioned into collection of sectors. And each track has a fixed number of sectors, and each sector can store a fixed amount of data. Usually data is stored on such tracks, so such sectors. But in generally, when we refer this memory arrangement or the memory management and so on, usually what we see is disk blocks rather than disk sectors. And this block is defined as a multiplier of a sector. Or in other words, what we call a disk block is a one or more sectors. And when we store data on this disk, as we know, data can only be stored on persistent storage as files. And therefore, what we store on this disk are the files. And then the file may be accompanied, or in other words, the capacity of one sector may be sufficient to hold one particular file, or maybe multiple sectors or multiple blocks may be required to accommodate a single file. In that data are stored on this disk. And then we also look at an example where how can we compute the capacity of track, capacity of a surface, and the capacity of the disk and so on. And also we discuss when we accessing data stored on persistent storage, there are two factors get involved in this access speed, or in other words, access speed of a disk depend on three factors. That is the seek time. Seek time means how long it takes to move the disk head to the desired track, or in other words, just above the target track. That is the seek time. And then in order to read or write data on the disk set should be at the beginning of the target sector. And therefore, secondly, the disk should be rotated until the beginning of the target track comes just below the disk head. That is what we call rotational delay. And third one is, the final step is, we have to pass that target track from beginning to the end, then only we will able to read the data. That is what we call read time. Therefore, overall access time is defined as the total of seek time, rotational delay, and then the reading time. Because this rotates in a fixed speed, this reading time cannot be minimized or maximized. But obviously, rotational delay and the seek time could be maximized or minimized depending on the location of the disk arm currently, and then the location of the target sector, and those kind of things. And we discuss an example and see how these values can be calculated. And then we also talk about, when we talk about this automated database management, how we do it. For that purpose, obviously we need software. We have to achieve it through software. And then if we have any software, any piece of software that facilitate us to store and manage database. Or in other words, to store data, read and write data through a particular software, then we say that it is a database system. And an example we cited there is any high-level program or any program written in a high-level language with file processing capabilities. Like the C program with file processing capability, Pascal, Java, or anything, doesn't matter. The other one is, due to the demand in processing data, automatic data processing, a special purpose application softwares have been developed and used, and those are DBMS, or the database management systems. Those are special purpose application software. And then this DBMS approach came due to the several limitations of this file processing approach. We discussed those limitations, but with DBMS, those limitations are not there. So that is why we use this DBMS for database management. And when we talk about this DBMS application software has been designed to achieve a particular objective. So basically, what is this particular objective is the data independency. Data independency. What is the data independency means? Whenever we want to process data, the data should be independent from the way we process it. And we talk about this data independency in detail later. To achieve this data independency, DBMS has been architectured into three particular levels. And then these three levels facilitate end users to access the database. And then also it also provides the minimum effort of the database designers when they design the database logic, and then they modify or refine the database logic. And in addition to that, this also facilitates storing our data on electronic media and facilitate users to access them, what we call retrieve or update those stored data through this three-level architecture. And the three architectures, usually that's called ANSI Spark architecture, and three levels are known as external level, conceptual level, and then the internal level. What is the external level is, as we discussed last time, when we construct a database, let's say there is a already constructed database like account database, student database, employee database, like database is there. And now we discussed last time, unlike file-based database systems, file-based database, this DBMS based database, so in other words, database created based on this DBMS, the multiple views are possible. So in other words, different end users can look at our database differently. In fact, there is a one global view of the database. The global view of the database means the entire database. But in addition to that, different users can look at it differently. That is what we discussed last time. When we have the account entity, manager has a different view, account representative have another view, and then the general customer and the teller has another view. And that kind of all the views of end users is known as external level. And then these external level can be considered as a collection of application softwares written to access this particular database. Because the different user write his or her own application based on his view of the database. But though it is the case, actual database, there is a core. We have what we call it, there is a database logic. There is a database logic. That database logic defines what kind of data to be stored and how those data relate to each other, because we define the database as stored collection of coherent data representing a particular mini world. And therefore that representation of the mini world concern is what we call database logic. That database logic is in conceptual level. And then there is a user view on our concept, but that concept is not sufficient for management of the data. For data management, they need to be stored on electronic media. Then internal level represent the actual electronic media where this database or data representing the database logic is stored, plus how such stored data can be accessed. So in other words, actual physical, we call physical storage, actual physical storage plus action mechanisms are the what we talk about the internal level. So internal level could be a collection of magnetic tapes, and then the access mechanism is obviously sequential access. But whereas if the physical storage is collection of disks and then the access mechanism, there are two, sequential access as well as the random access. Okay, this is the graphical view of that. And then here you can see that physical, this internal schema is this data, whatever the physical storage where our data is stored. And then this conceptual schema is the what we call actual database logic. And then the external level is the collection of views by the different end users. And now, but having these three levels is not sufficient ideally. Because now assume that now data is stored in this physical disk, and then internal level consists of that disk and internal schema. Internal schema describe what kind of storage media is used. That means the tape, disk, compact disk, or whatever it is, plus what are the access mechanisms, that is the sequential and random or sequential only and so on. That is the internal schema. Conceptual schema is the database logic what we talk about. That is where we explain what are the pieces of data we stored, how they relate each other, whether there are any restrictions in accessing them, and all those things are conceptual schema. But this is only the graphical view. But just assume that the particular user, just say here user 3, want to access this database for retrieving or updates. And then the user 3 want to access it. User 3 can't directly go to this disk or the tape. Then what is the user 3 should do is, it should access it through this conceptual schema. That means the user can access the internal schema through the conceptual schema, because this user 3's application program or view 3 that is written based on this conceptual schema. And that is why it is going through these levels, all from top to bottom. You can see that this association lines here, and what that means is each view should have association with conceptual schema. Conceptual schema, only one conceptual schema is there for any database that have internal schema of the same database, and then internal schema has the association with physical storage device. And therefore, when a particular user tries to access the database, then interaction among these three levels is essential. Interaction among these three levels is essential. And in order to facilitate between these three levels or schemas, two mappings are provided. Or in other words, to achieve the interaction between the conceptual schema and the internal schema, a mapping known as conceptual internal mapping. Conceptual internal mapping is there. And similarly, to facilitate the interaction between the external level and the conceptual level, there is another one, that is external conceptual mapping. Those two mappings facilitate the interaction. Or in other words, three schema architecture of a DBMS is not only these three views. These three views plus those two mappings together facilitate this overall interaction law that define this three schema architecture. Then you can hear these are the three levels, and now rather than the user view, it says external schema, that is the user view 1, user view 2, likewise collection of them are there. One conceptual schema is there, one internal schema is there. And then in addition to that, there are two mappings as I mentioned, external conceptual mapping and the conceptual internal mapping. And now, why we use these two is, at the beginning I mentioned that main objective of designing the DBMS into three-level architecture is to achieve the data independence. Data independency. Or basically what is the data independency means? Any modifications to the database conceptual schema and then the external schema does not affect on the internal schema. Or in other words, that's what I made the mistake. What's the actual data independence means? Any modification to the conceptual schema and the external schema does not affect on these external schemas. Or simply speaking, once a user writes its application program, even there are minor modifications to this conceptual schema and internal schema, user still can access the database using the same application program. For a very simple example, just say the physical storage may be shifted from magnetic tapes to disk, and then this internal schema is modified. Why? Because the access mechanisms now is changed from 1 to 2. That is, initially because of the magnetic tapes, only sequential access mechanism was there, but now change of physical schema to disk, now two access mechanisms are there, sequential and random. That modification is there. And now also think about in this conceptual schema, initially when we store a particular entity, just say student entity, initially we stored age attribute. Initially we stored age as one of the characteristics, and later, and then this external schema of the application is written by looking at the age value, but later this age characteristic is changed to the date of birth. It is changed to the date of birth or the other way around, date of birth or the age. Then what happens? Now application is written by looking at with the age as a value, but the conceptual schema now age is not there, only date of birth is there. And now this date of birth is available, age can be computed by subtracting the date of birth from the current date. That is achieved through this logical data independence. this mapping. This mapping facilitates that adaptation. And similarly here, if this access mechanism is changed, then this physical data independency, or in other words, this particular mapping, manage that change to the internal schema. That means a change made to the internal schema is managed by conceptual internal mapping, and then any modification to conceptual schema is managed by the external conceptual mapping without affecting the user programs. That is what we call data independence. But if we partition this database data independence into two, that means in case of the data independency, we do not talk about where the modification is made, whether it is to the concept or the physical storage. And then if we talk about only our modification is to the internal schema, then we say that it is the physical data independence. In other words, the physical data independence means even the internal schema is modified, application programs can access the database using the application program without modification. Logical data independence means if we make modification to the conceptual schema, but still application programs can access the database without modifying it. That is what we call logical data independency, that is about the modification to the conceptual schema. Physical data independence means modification to the physical storage. And we talk about this internal conceptual. Okay, now we talk about what is the external view and the internal view, but what we have to concentrate more is about the database logic or conceptual level. And in this particular level of this conceptual schema consists of logical structure of our database. That means the entire database, or basically speaking, the so-called mini-world. That the entire representation of the target mini-world should be here. Target mini-world should be here. Because of that reason, and then in this conceptual level is usually independent of that kind of or type of storage media we are going to use. Whatever the storage media doesn't matter. Only thing is that is digital storage media. It could be magnetic tapes, it could be disk or compact disc or whatever is irrelevant here. And now, in order to define this conceptual schema, and then we have to have the overall representation of the minimal. And therefore, what we have to do is, this conceptual level should contain all the entities within the minimal, and what are the characteristics or attributes of those entities, and how those entities relate one another. Those things should be represented by this conceptual schema. In addition to that, if there are any constraint on those data, that should also be considered here. And for example, just say, whenever we have a manager entity, and one of the constraints might be only one manager per bank branch, only one manager per branch, something like that. And then also security and the integrity of the information. And then these things will be discussed later, this integrity constraints and so on. But conceptual schema consists of the entire representation of the mini world, and then any constraint applicable to that particular mini world, and then the security and the integrity of the information within the database. And external level, we already talk about these things. That is the user perspective or user view of the database. And when we say the user view, and there are few things to be considered, we say that for that banking example, what we talk about is how the particular user can see the database in terms of the account what we talk about. In a way, it is not only just the view, but there are, and then in addition to that, it also talk about the level of security as well. For example, and if we let any customer to open and or create and delete an account, then there is no security that people can modify. And similarly, if we allow the teller and the customer to modify the, update the balance, and then update the balance. Update the balance means obviously when they let them deposit and withdraw, balance is update. But for example, just say for a particular teller might make a mistake in entering the withdrawal amount or deposit amount, and then the update of the balance becomes incorrect. For example, when a customer hand over a slip to withdraw or deposit 100,000 rupees to the account, if the teller entered 10,000 by mistake, and then the current balance is updated with only 10,000 instead of 100,000. But in that case, even the teller identified that mistake, teller is not allowed to correct that. But in order to correct it, teller should communicate with the account representative, that is the one who has the permission to do so, and do it. That is the kind of security levels also defined in this external level. And we already talk about this objective. Objective is to achieve the data independence. And here what it shows in the difference between the three levels. And you can see that the conceptual level, this is what defined in terms of the programming. And then that is what we have stored in the physical level. There is an index. So we discussed index for facilitating the fast access of databases. And this is the internal level. You can see that actual the global view of the database, there are 1, 2, 3, 4, 5, 6 attributes. But when it comes to the external level, the first view has only 5 of them, second one has 3 of them, but when if you look at the third one, it may have only 4 or 2 like that, conceptual level. But in the internal level here, the how we store data on the physical storage is the internal level. In this particular case, it is stored as structure with index facilities. But sometimes it might be objects. In object-oriented database case, it could be object like this. So in other, how we manage data in physical storage is what we really talk about internal level. And we discussed these two mappings between the two levels. 3 levels are there, but the overall architecture consists of 3 levels plus 2 mappings. Mappings facilitate the interaction between levels. And we also talk about the logical data independency and the physical data independency. Okay, now when we shift to the database approach, and then usually when we want to manipulate database manipulation comes to this one, and in the DBMS approach, provide a particular language component in order to manipulate the database. When we say manipulate, it consists of the definition of the database, it consists of the access of the database and everything. And then basically that is what you talk about this structured query language or SQL component of a DBMS. Every DBMS comes with a language component known as SQL. This SQL generally consists of 2 language components. One is called data definition language or DDL, and the other one is the data manipulation language DML. And in generally, this data definition language facilitates the construction of the database. That means they define the database structure and then store the relevant data. And when we say define the structure of the database, that consists of the defining the entities, attributes, and then the identification mechanisms like what are the unique attributes and so on, plus what are the constraints applicable and those things. And finally, to store the data. After that, once the database is constructed, then it is ready to use. And in order to use it, or in other words, to manipulate it, there is a separate component known as data manipulation language, or DML. That is where we have this query facilities. That means we ask questions and then the DBMS respond with the relevant information. And then also there we have to have the security, or in other words, we call access control. And before we come to this point, I would like to discuss a bit about the security. Can someone tell me what does mean by a security? Do you hear me?
Limit the access to the only authorized people.
Allow access by only authorized people.
Access to authorized people.
So that is the authorization, for example. And then if you are using, or if you are, just say if you are an employee of an organization, and then in that particular organization, entrance door has a digital lock. You have given a digital card. In order to enter the building, you have to swipe your your electronic card at the door, and then the door is open for you, right? That is the authorization. If you don't have that digital card, you will not be allowed to enter the building. That is the authorization. But that is only a part of the security. And then there is a few more. Just assume that in your organization, once you use your digital card and get into the building, and without knowing the other people, you will steal something from the wherever you are, and safely you are going out from the building. Is there a security then? Just say you unplug the mouse from a computer and put it into your bag or pocket and go out. But still you are an authorized person. Then is it secure?
No, sir.
No. And then the one part is authorization and the second one is called access control. Or in other words, even you are authorized to access the whatever the overall system, but within the system, there are further control in accessing. For example, the best example in the banking application is customer, account teller, account representative, deputy manager, everybody is allowed to access the account database. Or everybody has authorized to access the account database. Once the authorization is granted, then everybody is not allowed to access each and every record. For example, teller and the account representative and the customer may not be allowed to access the loan records. Loan records can only be accessed by the loan representative and the two managers, deputy manager and the manager. And there is a control law there, right? And then because of that reason, we should have access control. And similarly in the case database, as I already mentioned, in the database may have multiple entities, and then the different users may have different privileges for access in them. For example, some users may allow to insert data into entities, but some others may have privilege to insert and update. And some others may have only retrieval permission, that is only read permission. That is how we control the access. And then by achieving or the providing this control access or access control, that allow us to provide the, or in other words, to have a better security, and then the control, the integrity, that means the correctness of the content of the database, and then the concurrency control, that means when the multiple users access at the same time, how to control the system without bringing the database from consistent state to inconsistent state, plus whenever the failure occurs, how to recover the database like things. In order to achieve these things, then we have to have a access control mechanism as well. And in addition to that, in terms of the security, authentication is there, access control is there, but still that is not sufficient. And then there should be a monitoring mechanism as well. And for example, just say we do everything, but still what we call capable or intelligent, capable, skillful people still can go through this authentication and the access control mechanism. And if something like that happens, or in other words, if there is a security violation by enemy or whoever, or that security violation may be by an authorized person or unauthorized person. But if something like happens, then system should be able to detect it even the later on, and then finally make prevention mechanisms so that such things will not happen later on. Such things will not happen later on. And then one of the popular monitoring mechanisms what we use is couple the things with the CCTV cameras. And if there is a security threat or security violation, and then we use this CCTV footage and check whether who is the people involved in and so on, and later on we will take the appropriate approaches. Anyway, that is about the security, and because of that reason in DBMS provide the authentication as well as access control. But in addition to that, we talk about there should be a multiple views which is not available in the file processing approach, and different users should be able to look at the overall database differently. That is what we call view mechanism. But view mechanism means depending on the end user's interest on the database, different views can be generated. And then view, as we already discussed, this view allow different users to have their own views of the database. And then obviously when we generate set of views, and that is the view is basically part of the database. And therefore if we create several views of the global database, and then global database means global view, and then those things becomes a subset of our overall database. And then what is the advantage of these views is that's provide the kind of the level of security, because then user access only what he or she need or interested. Others are not touched or accessed. And then in addition to that, it will provide a kind of customization of the appearance or the view of the database. Though there are thousands of entities within the database, if one particular user interests only on 2 entities, and then he or she access only those 2 entities and not doing anything with respect to the rest of the things. And then we already talk about this the DL and the DML. And then the other one is the non-procedural DML is also there. And then here, in this case, users, they can state what data needed rather than how it is to be retrieved. In other words, for example, here this DML, because the database is structured, the DML allow accessing or retrieving data by considering the structure of the data, structure of the stored data. But in non-procedural thing, you don't need to explain what is the structure. And then what we talk about is we can state how to retrieve only. Sorry, we state the state only, but we are not talking about how to retrieve the data. That is not necessary. But in the procedural DML, that allows user to tell the system exactly how to access the database. But non-procedural one, no need to say that exactly how to access or manipulate. And then when we talk about the database applications, okay, now and then this database applications means when managing data, different people want to manage data for different purposes or maybe for different objectives. And depending on that, different type of database are known as database applications. So in other words, mainly this application categorization is on what is the basis of creating and manipulating a particular database. And the smallest database application what we talk about is personal database. And the next level of the database application is known as work group database. And then when we go further, then departmental database, and finally enterprise database. Or in other words, in this slide, these database applications are written or listed based not only on the, basically these applications are based on the purpose or the objective, but this listing is mainly based on the scope of the database. Scope of the database. That means the what is the, basically you can think it as the how large the database. In that case, but this slide shows is smallest one is the personal one. Next one, work group, it is bigger than personal one, but smaller than departmental. And when we come to departmental one, it is bigger than the work group one, but smaller than the enterprise. Enterprise database is the largest database application we are talking about. And when we talk about the personal database, or in general, these personal databases are created targeting a single end user. Or in other words, some people may want to create the database for their personal usage. And then nobody else is authorized to access this database. Only one person is accessing it. For example, is a salesperson want to keep track of the customer information with contact details. But that doesn't mean that the customers are accessing that. Only salesperson access this one. And now, I hope all of you use digital devices. And can you tell me an example for your own personal database you are using?
Calendar application in PC.
Yes, okay. Calendar application.
Contact.
Yeah, that is the calendar application. Calendar application without sharing, right? If not, even you have a calendar, and if you grant permission or authentication to another person, they can edit to a calendar. Am I correct?
Yes.
Then it is not personal. Then what we have to do, calendar without sharing. What else?
Contacts in mobile device. Contact.
Yeah, that is the best example. That is the contact list of your mobile. Contact list of your mobile, because you keep the contact information of your whatever people, friends, relatives, or whoever, in order to communicate with them whenever necessary. But that doesn't mean that they also use your contact. They may have different one, their own. That's different thing. And the two examples are the calendar without sharing, and then contact list of a mobile phone. And the next application is the work group database. And then that is the relatively small, but the relative that is created not for a personal usage, but the smaller group of people, a smaller team of people, and generally we assume that less than 25. And then, for example, just say that, and then you create a WhatsApp group. We create a WhatsApp group including members less than 25. And then, for example, just say in a particular course in this program, then your instructor may ask you to group yourselves into 5 groups. Then, according to the number of students enrolled, each group has less than 10. And then only for communication among those people, you create a WhatsApp group or a particular database granting authorization and access control to all the group members and maintain that particular database. Then that becomes the work group database that can be shared by all the members of that smaller team. And you can see in this slide, and one particular example is team of engineers maintain versions of artifact that they design. Or in other words, each of them create designs, and then design is something, design is a solution to a problem, but for the same problem, multiple designs could be, and therefore different designers may come up with different designs, and then all the team members share those designs and may select the best out of all of them, something like that, or that kind of things. And this next one is the departmental database. And then usually this department database is created to share the data and information among members of a particular unit of an organization. Unit of an organization means it is bigger than the work group. For example, just say, when we talk about the particular organization, there may be departments like sales department, human resource department, purchase department, accounting department, and so on. And if there are databases, if there is a database created for sharing information or data among that particular department members, then it is a departmental database. But in addition to that, there is another way of doing that. That means when we talk about the size, when we come to an educational institute, and then rather than only to a department, and for example, a database might be created for faculty members. And then if the university has 5 faculties, 5 separate databases are used by each faculty. That is also a departmental database. I'm just talking about, I mentioned this scope. In the previous example I mentioned, scope is smaller because the database for each department. But now database for each faculty, that is the bigger in scope, but still it is below the enterprise database. But the enterprise database is, as I said, that is the biggest one we talk about. There is no time scope limitation we discuss here, but that is the database created to share data or information among the enterprise people. That means among everybody within the enterprise. For example, if we create a database for a particular university, and that is an enterprise database. The scope of this enterprise database depends on the mini world what we talk about. For example, when we say the enterprise database, on the one hand, this enterprise could be the Sampath Bank, but another enterprise database might be the People's Bank database. But if we don't think the banking industry in general, regardless of the private banking and the state banking, if we put all of them together, that becomes the banking industry. That is our mini world. And then if we create a database show that all the stakeholders of the banking industry can access that particular database, that is the one of the bigger enterprise database. And that is where we are now, because now we don't need to worry where our account is maintained. We can access it through BOC ATM, People's Bank ATM, Sampath Bank ATM, Commercial Bank ATM, or whatever. That is because our enterprise database scope is bigger. And if we talk about the largest enterprise database available, can you tell me what it is? Largest enterprise database available. Google, because everybody is now, but Google is the one large one, but even bigger one is there.
Facebook.
It is
Facebook.
Facebook is still like the Google, but where are all those things? When you put all of these together, what is it? Where Google is available?
Web?
Internet, or
www.
rather selling internet, it is better to say World Wide Web. World Wide Web. Right? And that is the biggest database we have. Because the applications you mentioned, Google, Facebook, Twitter, whatever you mentioned, those are part of the World Wide Web. Okay, now what we talk about so far is database application. And the next one is when these requirements of data management is evolved. In other words, the people want to manage more and more data. And then this database, even the enterprise database, might not be sufficient to meet the requirements. Then we talk about data warehouse. And then what is this data warehouse? That is still an enterprise database. Sorry, that's what we need the database, because even we say that an enterprise database is the biggest, sometimes except that World Wide Web, and then the databases, enterprise databases created by database designers may not meet the requirements of the all the stakeholders. And therefore what we do is we move to the data warehouse from databases. And then what is the data warehouse? Ideally, data warehouse is an integrated decision support database. Integrated decision support database, and its content is derived from various operational databases. And there what you can say is, you can view this data warehouse as a composition of the enterprise databases. Composition of the not only enterprise database, a composition of a collection of databases. And then users can access data or retrieve data from all of those databases. All of those databases. And then if we talk about what are the main advantages of this database approach. Here database approach means DBMS based databases, because the file based database is also a database approach, but now we are not talking about it, but now what we are talking about is constructing database using DBMS. And then the one of the advantage is it is easy to maintain because the program data is independent, because we said that three-level architecture facilitates the data independence. When there is an independency, it is easy to maintain. But if they are dependent, obviously it is hard. And then as we mentioned, file-based approach has data redundancy. We can duplicate things unnecessarily, but in the DBMS, allow maintaining only minimum redundancy, or in other words, allow only to duplicate essential data. And then they improve the data consistency, how it is improved. And whenever we try to access the database for inserting, or in other words, the updating purposes, then it will check whether whatever the data users trying to insert, delete, update, or whatever is sensible. And then only it is allowed. Otherwise, it is not allowed to perform such operations. For example, just say if we have an attribute or data item called the age, and if we define it according to the metadata definition, it is a number. And if you try to enter text, it will not allow you to enter text as a number. But the other way around is anyway possible, because the number is a collection of character, and therefore you can enter a number as a text-like thing. But anyway, inconsistent things are not allowed. And then the data sharing is improved. Why data sharing is improved? And because unlike the file processing approach, multiple users can access the database. That is, multiple users can access the database, and therefore sharing is facilitated there. And then the productivity is increased when using the database, and we have structured the data properly and stored them in consistent manner, and therefore whatever the access by the users, and then that is meaningful, and then they can access meaningful and the correct data without any inconsistencies or delays and so on. And because of that reason, this database improve the productivity. For example, very simple example for this one. And then if we have a database to support our farmers, they can access the database through their smartphone or mobile phone. And when they have the issues regarding this cultivation and so on, they can access to the database, and then they can get the relevant information and then apply those, whatever the techniques or whatever they find from the agricultural database, and that will improve their productivity. And then enforcement of standard, that again comes along with this structuring of data, and then we use the metadata to store data on databases, and then there is always a standard for defining the things or structuring things, and then the accessing, manipulating, or everything is done according to a standard. And then data integrity is improved, and that is where we talk about the integrity constraints. Those things will be discussed later. And then the users are not allowed to access the database for doing anything they want. They have to access them according to the enforced standard, and because of that reason, integrity is always there within the database approach. And then the improved data accessibility and the responsiveness, that is what we talk about in this SQL and other things. And in addition to that, this DBMS, you saw earlier that database manager, and this database manager has several components, and those components facilitate this data accessibility and the responsiveness in the acceptable manner. So that means whenever user make a request, and then when we submit the query is processed in optimal manner. optimal manner rather than unnecessary delays and so on. The best approach or the best path is used to execute the query and return the result to the end users. And improve the security we already talked about. Unlike file processing approach, DBMS also has its own security component, and that one plus OS security together improve the security. And then increase the concurrency, and that's also already discussed. File processing approach, only read concurrency is there. That means multiple users can read the files at the same time, but the writing is not facilitated. Whereas the DBMS approach, without any concern about how many more people are accessing the database, anybody can access the database for both reading and update. And this is what we talk about so far: improve maintenance to program data independence. And that is where what we talk about is the data description is done by defining the metadata, and therefore these descriptions are used for everything in database management, like the we call defining the data dictionary, and then the accessing data, modifying, and everything. And we all this data redundancy, because we allow only the minimum duplication. That means the only thing what we allow in database is to maintain duplicate entries as foreign keys which are required to relate our entities together. And then the consistency, when we don't have the redundancy, that means unnecessary duplication, hardly the users are returned with incorrect data rather than incorrect, unnecessary or unexpected results. Like what we talk about, whenever the users access data regarding the Kamal Disanayaka, if the system returns the values regarding the Kasun Disanayaka, that is what we call inconsistency. But if because everything is properly structured, and then the storage and the everything is done according to the standards, and then when we retrieve relevant data, the data is consistent as far as unnecessary duplications are there. And data sharing, that is the pretty straightforward thing. Multiple users can share the content of the database, and then we already talk about this, the productivity by considering that farmers example, enforcement of standard, and then because of this standard, nobody want to worry about the content of the database as far as they are not doing unauthorized or unnecessary things, because the database administrators enforce the standard for database sharing. Like we talked about earlier, then they will define who is authorized and who has the access rights and all those things. And then the integrity we already talk about, like when we enter data, the correctness of the data is stored in the database and or update or whatever. Those things are checked for the validity, and then only it is allowed. And then the improved data accessibility and responsiveness, we already talk about with the database managers and the other components involved in the DBMS. They make sure that the accessibility is according to the expectations of the end users, and also performance is acceptable level. And then the security also, we already discussed that. DBMS itself provide the security facilities. The concurrency, and then we already talk about DBMS approach allow the concurrent access for reading and writing both. But obviously in case of the writing, later on we discuss, though concurrent writing is allowed, that need to be controlled. Otherwise, database may bring from consistent state to the inconsistent state. Those things need to be controlled. We talk about those things in later. And then whatever we talk about, this is not only DBMS, whatever the computing aspect we are talking about, nothing is perfect. And that means we can't say that it is 100% perfect application, no 100% perfect computing approach. Everywhere there are pros and cons. And similarly, the DBMS also have their own limitations or disadvantages. One of the disadvantages is the complexity of the DBMS. Because when you store data, or simply we say, when you construct and manipulate databases, and you have to follow standards, like you have to first define the metadata and then create the database structure, and then accordingly you have to store data, and then you have to define your user use based on the conceptual schema, and all those things are adding the complexity to the DBMS approach, and therefore complexity is there. And next one is the size of the database, and then we even talk about the triple W, and then when the from personal database to the enterprise database, the scope or size is increased, and therefore that will, when the things become bigger and bigger, obviously difficult to maintain, and therefore it is also a disadvantage. And in addition to that, this, except the sum of these application softwares, the majority of the DBMSs are proprietary software. That means you have to pay and get it. Like the SQL, Postgres, like few open source applications are there. Those are sufficient for educational purposes. But for developing the large enterprise applications, this MySQL like things are not good enough, and therefore then we have to go for commercialized DBMSs like Oracle, MySQL Server, like DBMSs should be used, but those are proprietary, therefore we have to pay for them. And then in addition to that, additional hardware cost is necessary. Obviously nowadays this is the general thing, but nowadays we have two approaches. One is we can have our own hardware, the database servers, file servers, web servers, like those things for our own. But in a way, that means we have to purchase the hardware to maintain the DBMS. On the other hand is, nowadays, rather than purchasing our own, we can hire. We can hire through the clouds. Right? Then you can hire this infrastructure to pay for just usage and approach it, but still the cost is involved there as well. And then the next one is the cost of conversion, and then then when the user requirement get changed, and then whatever the presently used DBMS may not be good enough to maintain or manage the data, because the one hand requirement is evolved, on the other hand the amount of data to be managed is ever increasing, and because of that reason the available or currently used DBMS may need to be we call migrated to another one. Therefore the conversion might be required. Then once again it is also costly. That means the particular cost factor is there for that one. And the other hand is performance. And when the DBMS is managing a very large databases, then in addition to that, the user base is bigger. That means the large number of users are accessing the database, and then the performance issues arise. Performance issues arise. That means they may not give the required information quickly. It may take some time. And those kind of performance issues are also there. Moreover, because we are maintaining all those things or managing all these data using the computing facility, computing technology, because these computers or machines could fail any time. And because of that reason, there is a high probability or possibility of failing the systems. And those are the disadvantages. Okay, that's about the in general topics about the database management, or what we call database systems. And now we move to the point of designing. Or in other words, now we talk about in the general things, but next we look at how to construct the database. How to construct a database. And for that purpose, let me know whether, sorry, no, that's database design. Okay. Okay, can you see the slides?
Yes, sir.
Okay, now then as we discussed, in order to use this database, the first thing what we have to do is we have to bring the database into existence. That means we have to create the database. In order to create database, we have to design it first. What does the design mean? First, we have to have the abstract database. It is something like before building a house, we have to first prepare a building plan. Building plan. Building plan explains what kind of building we are going to build. But having a plan doesn't mean that we can use the building. In order to use the building, we have to really build in with, whatever the bricks, sand, cement, furniture, and so on. So that is the bringing our abstract solution to the concrete solution. Database is also the same. First, we have to design the structure of the database. And after defining the structure, that is same as the building plan, and then finally we have to convert or transform it into a digital media so that it can be used. Now what we are going to discuss is only to coming up with the database structure. That is what we call about the database design process. And then in order to design the database, the first thing what we have to do is we have to have a model of our database. And then we have to do is we have to just think about what kind of database model we should use it. And then basically that is what we say is first we have to understand what is the scope of our database. What is the scope of our database? And who are the end users? And what are the requirements of this database? And those things should be modeled first. That is what in, for example, if it is a database for a business organization, and then they have to think about, okay, this is the database we want. These are the people who are going to use it at the end. And then these are the functions should be provided by that particular application. And therefore, those things, that requirements and everything should be modeled first. And that is what we talk about data modeling. First thing is we are model data. After modeling data, then only we can convert into a database. First concentrate on data and then concentrate on database. And when we doing those things, and then basically when the good database modelers, the designers usually we call database designers, they always consider the principles of database modeling and plus, and then always they concentrate on the consistency of the data. consistency of the data. So that is what you see here at the normalization. We talk about it later in detail, and then we have to have the consistent set of pieces of data for modeling our database. And this normalization mainly concentrates on the redundancy. That means we should minimize the redundancy, and then we have to minimize the restructuring of data later on, and then also it should concentrate on the access time minimization. That is what your input output by reduction of transaction size. That means the what the operations we are going to perform over this data, and then also that should concentrate on the correctness of the data once operations are performed over the data we store. And then whenever we talk about this, the database model, just say database design, when we talk about the design, it is a solution for a problem. A solution for the problem. There may be many solutions for the problem. And then out of those solutions, some of those solutions, but if they are solutions to a problem, nobody can say that solution is wrong. Solution means the correct answer. Solution is the correct answer. But what we can argue is that solution provided to that particular problem may be good or may be not good. That is the only thing what we can say. We can't say correct or incorrect. If it is incorrect, it can't be a solution. Right? Solution means correct. And that is why we say poor database design. Poor database design is solution is there to our data management problem, but its quality is not good. And then that will produce several problems like inconsistency, performance issues, difficult for concurrent access, and all those things are there. But if we have a design which is poor, to make it a good design, then what we have to do is we have to send it through a normalization process. This normalization process is used to minimize those problems. Minimize those problems, and in most of the cases we try to eliminate rather than minimizing whenever possible. But it may not be possible to eliminate 100%. But obviously what we try to do is through the normalization, we will try to eliminate those problematic things or poor aspects and try to bring it to a quality design. And in general, in designing a database, to come up with a good database design, we go through 4 phases. The first one is what we do is we requirement collection and analysis. So that means basically before we construct the database, what we are given is a part of the real world or a mini world. A mini world is given and asked to construct the database or asked to design the database. But in order to design the database, you have to start with the mini world, and then you have to end with the good quality structure or good quality database. That is, I am talking about the database construction. And then in the database construction include 4 phases. First one is you start with the mini world and then collect the requirement and then analyze them. Or in other words, what that meaning is, look at the mini world, identify the entities get involved in, identify the characteristics associated with those entities, identify the associations among them, identify the constraints applied to those identified entities. That is what we talk about the requirement collection and analysis phase. And then the next one is conceptual design. In other words, we will define the concept of our database based on the identified and analyzed requirements. Analyze and requirement. But that concept may not be ready to transform into the electronic media. It gives the idea, this gives the idea or the rough, it gives the representation of the database. It gives the representation of our database, but that may not be possible to transform into the electronic media. And then by starting from that representative of the database, we convert into the logic of the database. What is this logical database design means? Starting with the concept of the database, we transform it to a structure, database structure, which is ready to transform to the electronic media. It can be readily transformed to the electronic media. When we define this, the database structure, one might discard or ignore this phase 2. They collect the requirement and then analyze them to identify those entities, attributes, and so on, as I mentioned. And then rather than designing its concept quickly from phase 1, jump to the phase 3 and define the structure of the database. That's fine, no problem, but usually these are the phases we follow. Requirement gathering, define the concept of the database, and then transform it to the logic of the database, that is the structure, ready to transform to the electronic media. When we complete the first 3 phases, then what we say is database abstract view of the database is there. Or in other words, abstract database is ready. Abstract database is ready, but still not ready to manipulate or use. But if you want to make it concrete, we call concrete database, means the usable database, then you have to complete the phase 4, that is the physical database design. The physical database design is the phase where we select the appropriate electronic media, disk or tape or whatever, and then we represent, or in other words, we define or implement the structure proposed by this logical design. Or in other words, the result of the logical design is the database structure. That structure is implemented within the electronic media plus store the sensible data following that structure is known as physical design. And once you complete all 4 phases, then your database construction is completed and ready to manipulate or use. Let's start with this requirement gathering part. What we have is we start with a particular mini-world, and starting with the mini-world, then we gather the requirements. And then this requirement may have 2 parts. The functional requirements may be there, and then the database requirements may also there. Some of them are database relevant, others are application or functional relevant. And then if you look at this database thing perspective, and then what we need is we identified the, for example, data view. What kind of data we are going to use in our database. In the functional view, what kind of functions performed over such data is considered. And then ERD entity relationship diagram, and that is the data view of our database. Whereas data flow diagram, that is the functional view. It explains what kind of functions to be applicable, operated, and what data to be passed from one operation to another, and those kind of things. And our concentration is the database design, and then after completing the database requirements, that's we identify the relevant attributes, relevant entities, attributes, and so on. Then we move to the phase 2, that is the conceptual design. In conceptual design, there, as I mentioned, that will give you a representation of the database. What are the entities, how they relate, and those kind of things are there. And then one example for this conceptual design is once you complete the data gathering part and analysis part, and now you have an idea about what kind of entities, attributes, relationships, constraints are included in your database, and then based on that, you can draw a entity relationship diagram or a class diagram or something like that, the representing the database. So that is what we call conceptual design. And then this conceptual is generally a diagrammatic representation. It is generally a diagrammatic representation. That's what I said. It could be an entity relationship diagram or a class diagram. And then once you complete that, and then we move to the logical design, and then the logical design is basically conversion of the conceptual design into a database structure. And in case of the relational database, this our concept is transformed into a collection of relations. Collection of relations that will become the logical design. That is where we talk about these entities, their attributes, and then how to relate them, what is the unique attribute for identifying the instances of those entities and all those things. And then, but basically what we can say is that is the blueprint of the database. Blueprint of the database means no data there, just the representative factors are there, and those representative factors are used to construct the physical database. The physical database. And the physical database is starting from the logical design, bring into the usable database, which reside inside the electronic or electronic media, mainly persistent storage. And this is what get involved in this thing. These are the four phases we talk about: requirement collection and analysis, conceptual design, logical design, physical design. And they are in between here, their requirement, database requirements are collected, plus functional requirement, both are taken together, and then the concept of database is designed, their conceptual data model is, and then it also includes the high-level transaction specification, that means what kind of operations to be performed over this particular database after construction. And then the logic is defined, and when we comes to the physical design, the logical data is converted to the physical data, and there we have to think about what kind of application programs are designed and what kind of transactions to be implemented, and those things are considered here. An overall picture covers the what we talked about earlier, 3 schema architecture of a DBMS. But this right-hand side is the mainly database design part, but database design is not totally independent thing. That should not only concentrate on the data aspect of the database, but also functional aspect of the database should also be considered. Otherwise, database is available, but when we manipulate it, the manipulation may not meet the functional requirements of our organization. And then over the years, the different database models have been proposed and used. And then the earliest one is, as we discussed, traditional file-based databases. And because that is in 60s, because of the limitations of the traditional file, and then they move to the, in 70s, they move to the hierarchical database model. That means the entities are related into a tree structure. And then later, even that is having problems, then the network database model, and that is also in 70s. And then their entities may relate not only vertically, but the horizontally also relations are possible. And then this network model is also in 70s. Later on, even better thing is was needed, and we identified, and therefore relational database was introduced. This is the most popular and widely used database model even today. That is in 80s. And later on with the introduction of object-oriented technology, then the object-oriented database model is introduced in 90s. Or the difference is the relational database model. Our entire database is a collection of related relations, whereas object-oriented data model is a collection of related objects. But due to the high complexity of this object-oriented database model, and then what's the later introduces after 1990s, started with 1990s, object relational database model is introduced. That means object relational database model is a integration or mixture of relational database and object-oriented database model. Then ideally, what is the idea here? Object relational database model is database is constructed according to the relational model, but the manipulated according to the object-oriented technology. Created or construct following the relational model and manipulated following the object-oriented model. And here you can see what I said. Usually conceptual data model is a diagrammatic representation, whereas logical data model is, you can view it as a mapping. It could be mapping, and not only that, it could be a mapping as well as a collection of maps as well as the diagrams. For example, in the relational databases, logical data model is a mapping, whereas object-oriented one, it may be a mapping plus diagrams. And then this is the physical model. That means how we store these things on electronic media, that is usually as tables. Okay, now to discuss further, you can have a 10 minutes break. Then after that we restart. Now it is 9:45. I will restart 9:55. And then once the data model is constructed as we discussed, then the logical data model is designed, or that is also done by the data analyst. So that is what we call core of the database. And in order to construct the consistent database, the database designer should pay more attention on the logical database, because all the applications and then all the user level applications and the performance of those applications and everything depends on the quality of the logical data model. Usually physical data model, or that is done by the database administrator, but obviously that is the physical database design depends on the available technology, because whatever the available technology, early days, like when the only magnetic tapes are available, then the physical database access mechanism was restricted to the sequential access. But now with the advancement of this computing technology, and now we can access both in sequential and random manner. So basically this is the database development's life cycle. And then first we have to identify what is the project and what are the requirements of this project, and then database is constructed for that, and then we have to initiate the project and the planning, and then we have to analyze. Obviously for the database part, during this analysis, we talk about, we mainly concentrate on this, how the project has been planned and what are the operations they have planned, and then that means the requirements of the project, and based on that plus data requirements, the analysis is completed, and then come up with the conceptual design, and then follows the logical design, physical design, and then finally implement the database. And once the database is construction, whenever once the database construction is over, then end users will start using it. But even while the using, and then the database, overall database management job is not over, and then there is a maintenance comes up. For example, in the database logic may need to be advanced or enhanced, and then we have to, for the enhancement purpose, then we have to modify the database logic, and then accordingly implementation need to be updated, or those kind of things. We have to maintain the database to make it a long-lasting system. Okay, this is the database development activities get involving enterprise modeling, that is the enterprise level, and then the conceptual modeling, logical design, physical design, implementation and maintenance as you saw earlier. In the enterprise modeling is the basically where we start, and then in general nowadays databases or data management is for enterprise level or organization level, and then the system analyst has to concentrate on what kind of data this enterprise is needed, and then identify the data requirements, functional requirements, and then it need to be identify how this should be proceed. And this is where very important thing. And when we identify an entity, there are so many associative characteristics may be there, but out of which attributes are essential for this enterprise application or a particular project, and depending on that, those relevant and the essential characteristics or attributes should be selected from the identified associated attributes. And then this is what the main thing is need to be done. Conceptual data modeling, as we already mentioned, we have to identify the scope of the database requirement, and that is basically minimal, and then we have to analyze overall data requirements. So that means which data is required to perform the expected business functions, and for that our database should facilitate, or our database should facilitate the data requirements of the business functions. That means data can be stored, but this stored data should facilitate performing the operations of the organization. Otherwise, there is no purpose of having even a 100% consistent database. And then we have to develop conceptual data model, and that is where we design the diagram, including the entities, attributes, relations, and so on. And then we develop the detailed one, that is the fine-tune it by including all the things required for facilitating the enterprise applications. And then finally we go for a conceptual database specification, or that means the logic of the database or database structure which can readily be transferred to the electronic media. And this is where we have to concentrate on what are the operations to be performed. That's what we call transactions. And then how to display data based on the queries. And then those things are concentrated or considered in designing the logic or structure of the database. And then also what kind of views are there, like we talk about in the banking application, multiple views are there. And then our conceptual data model where after the completing the conceptual data model, and then the logical data model should concentrate on the different views, and then what are the various integrity and the security aspects we have to include into our database. For example, if a particular table in a relational model, if the particular table is accessible only by a particular set of users, and those kind of things should be considered. We talk much about this physical database. It is just to transform database logic into actual usable database. This in the implementation, that is why we usually use that SQL first part, DML, data definition language, for defining the structure of the database and then storing the data onto the database. And then also there we have to, in any system development, we have to maintain the documentation and then the training manual, and that is all the things for the two things, that is to support the end users, and the other one is to support the maintainers. And then finally, implementation is also there. For example, database management system like the Oracle or SQL Server, MySQL or whatever it is there, and then before using it, we have to install it in our machine. In the maintenance, there are several aspects in maintenance. As I mentioned, basically maintenance is done to make it long lasting, and then though it is long lasting, whether the particular database is accepted by end users is depend on whether it facilitates the user requirement. And therefore, with the ever changing user requirement, the database may need to be enhanced to facilitate the new features. And in addition to that, if there is errors, there are errors, and then those errors should be fixed in order to make it usable again, and also to recover the whatever the loss occurs due to the failure. We talk about the conceptual design. Okay, now when it comes to the conceptual design, and then what we talk about from here onward is the how to perform this conceptual design. As discussed earlier, the first thing what we have to do is that we have to analyze the mini-world and then identify the entities. And in this particular example, you can see that 4 entities have been identified in this particular project: department, employee, project, and the dependent. And then we have to identify what are the relationships get involved in those identified entities. For example, department and employee are 2 entities already identified, and then it relates like this. A department has many employees. For one department, multiple employees are there. And then an employee works for department. That means the one employee works for a particular department. One department may have many employees, but each employee is work for a particular department. And then relations, there are different type of relationships, and those are known as unary relationships, binary relationships, and ternary relationships. And then the relationship is basically what is the meaning of association between one or more entity types, so that is entities. And then the relationship instance, what we talk about is association between instances of entity. And then instances of entities. Then for example, the Silva works for personal department. There may be multiple departments, but the personal department is one instance of a department. And this is what the same relationship what you saw earlier. An employee has many dependent departments, and each department belongs to an employee. And then another one among the same entity, that is in this one, Here, two entities are different. Employee, dependent. Employee has, no, this is not the previous one. Sorry, I made the mistake. Previous one is the department and employee. Now it is the employee and dependent. One employee may have multiple dependents, but each dependent belongs to a particular employee. And then in both of those two examples, the two participating entities are different. Earlier, department and employee, now employee and dependent. But if you move to the next one, third one, now here, the participation entity is the same. An employee, an employee. What it says is an employee supervised by an employee. That means each employee is supervised by another employee. An employee supervises many employees. So that means it seems that among the employees, there is someone called supervisor. That is what we, among the employees, one of them is a supervisor. That supervisor supervises many other employees. That is, this one is the relationship between the same entity. Other two are relationships between two different entities. And then entities and relationships. And then here going further, a company has many departments. And then a department has many locations. Then likewise, when we consider the particular mini world, and then each identified entity may get involved in multiple relationships. Some of them may be self-relationships like employee and supervised employees, and some others may be association among different entities identified. And then here is further, that is what we talk about is, here what you can say is one-to-one relationship. There are several relationships what we talk about, out of which if we consider binary relationship between two entities, if we consider a department and each department, that is the department, sales, personnel, sales, manage employees, and employee manage the department here. This is what you have to look at. An employee manage a department. This means for each employee, for one particular employee is responsible for managing a department. Similarly, for any department, there is a particular employee managing it. Then we say that one-to-one relationship. It is something like, for example, if we consider there is one DVC for a university, one VC for a university, and also for each university there is only one VC. There is a one dean for each faculty, and for each faculty there is a one dean. Those things are one-to-one relationships. But when we say one-to-many relationships, in a one side there is only one instance get involved, whereas the other side multiple instances get involved. This is what we call an employee works on many projects. The same employee can work for many projects. But when we consider a particular project, that project is associated with the employee, one-to-many relationship. And here, a project controlled by a department. And in this particular case, there is a project which is controlled by department. And then this department may control multiple projects, but each project is controlled by a particular department. It is like the university can have multiple faculties. University can have multiple faculties. One university, but multiple faculties. But each of such faculties belonging to the one university. Each of such faculty belongs to a one university. And also a father can have many children. Father can have many children, but each of those children, each of such child belongs to that particular father. There is one-to-many. One-to-many. One side there is only one instance get involved, other side many. Other one is many to many. In both the site, multiple instances get involved. And then, for example, in the construction and delivery in the project, and then the construction side, there may be many construction and there may be many deliveries. But the best example to understand this one is the relationship between course and student. For a one course, multiple, I don't know whether, give me a minute, I want to, this is what, okay. Okay, when we consider many to many relationship, and then both the sides, there are multiple instances get involved. And then here, this one, when we talk about this one-to-one relationship, instance of one entity associate with at most one instance of the other entity. That is true for both the directions. That is what I mentioned, Vice Chancellor and the university. For one Vice Chancellor associated with only one university, and one instance of the university associated with at most one Vice Chancellor. That is why we call one-to-one. But in case of the one-to-many, one instance of the one entity associated with many instances of the other entity. That is we call university and the faculties. For one university associate with many different faculties, but each faculty associate with one particular university. And the next one, what we talk about, the many-to-many, I mentioned course and student. For a one course, there might be multiple students there. That means the multiple students follow the same course. And not only that, for a one particular student, they may follow multiple different set of courses. And in that case, for a one student instance, multiple course instances get involved, as well as for one student instance, multiple course instances get involved. And then those are the things what we have to understand in conceptual design. And in order to come up with the conceptual design, as I already mentioned, usually conceptual design is a diagrammatic notation. And therefore, when we draw the diagrammatic notation, and we have to understand how we draw a diagram of the pictorial representation. For designing a pictorial representation or drawing a diagram, we need a language known as modeling language. This modeling language is a collection of symbols. And then in order to draw the diagram, we have to have a process as well. But the modeling language does not provide this processing part that should come with the designer. That means if we are drawing a diagram, we have to provide the contribute to the process part, but we use the modeling language, that is the collection of symbols. And for example, if you are drawing the circuit diagram, there are certain symbols to use for the circuit diagrams, and then you take those appropriate diagram symbols and then connect them through to a diagram by contributing your part as the process. Here also the same. In order to design the concept of the database, usually we design the entity relationship diagram. For that we use entity relationship language, where in this entity relationship language is a collection of symbols to represent various aspects of this database design. And then those symbols or notations we use, for example, if we use an entity, this entity is represented with the rectangular box. If it's a relationship, we represent it with diamond. If attribute, it is an oval. Then you are familiar with this thing. And then there are three types of relationships: one-to-one, one-to-many, many-to-many. But in this particular case, what you have to consider is, even for the entity relationship modeling, there are multiple modeling languages available. Multiple modeling languages available, and those languages differ one another with the minor notational variations. Minor notational variations. This slide shows one of them. And then if it is a one-to-one, then the two entities get involved, company and employee. You can see that those are represented with label rectangles, and the relationship is the director, and then company, director, employee, and then there is it is a one-to-one relationship. Therefore, only two line segments are used to connect the relationship and the two entities. If it is one-to-many, how it differs is the entity where multiple instances get involved, because company has multiple employees, and therefore only one company, multiple employees get involved, and therefore this multiple size entity, we use an arrow. We use an arrow to indicate that for this entity, multiple instances get involved for this particular relationship. Then many-to-many case, both the entities, the multiple instances get involved, and therefore both the sides of the line segment, there is an arrow. And the next one, that is the cardinality constraint, and that is specified number of instances of one entity can be associated with that particular relationship. The minimum cardinality, the minimum number of instances of one entity that may be associated with instance of another entity. And then for example, one-to-one case, maximum is 1, cardinality, maximum is 1. Either side there should be a 1. And then there are optional participation. That means there might be a relationship, but there could be no participation from one entity. That is what we call optional, and therefore in that particular case, cardinality might be 0. Cardinality might be 0. In the case of the mandatory participation, both the entities should participate and then number of participants is 1. And then the maximum cardinality, the maximum number of instances of one entity, that may be a single occurrence of another entity. This is how we divide. Employees can have insurance policies for at most 2 dependents. That means employee can have insurance. That is, employee may have insurance or may not have. If employee does not have, then 0 cardinality. But if the employee if employee has that, and then the maximum possible insurance is 2, and therefore that is why 0, 2. That is the employee entity size, cardinality is 0, dependent entity size, cardinality is 2. And this is the existence condition, that should exist here one-to-one, the company should be there. Why this existence constraint or condition? Without company, you cannot talk about employees. There could be a company without employees, that is okay. But there cannot be employee without company, and therefore company should exist first. And one-to-many case, once again, the same thing, you can see that only cardinality is different. Company should exist to talk about the employees. Without company, no way we can talk about the employees. Here, company. ABC Limited should be there, then only we can talk about this Silva, Das, Pereira or whoever. And this is again that this white colors oval indicate the existence. This is the ER diagram what we have written, and then the employee supervise. And that means if the employee has to supervise, what is this says is one employee supervise many other employees. But in order to supervision happen, employees should exist. That is why both the end this oval is there. And then employee has dependent. And then this dependent, in this particular case, dependent should exist. That means every employee should have at least one, so employee should have multiple dependent. And here employee works on project. Employee can work on the project only if project exists. If the no project exists, employees cannot work on that. That is why this one. And then employee manage department. The employee cannot manage department if the department is not exist. Not exist here. Department control project. Department can control project only if projects exist. Otherwise, it cannot. But here also you can say that here employee works department, there is no existent thing. That means the only other relationship there is a existent condition, but for this one it is not essential. And this is a representation of this cardinality. You can say that 1 to 1, this vertical line segment will be 1, and if this vertical line segment connected to 2, angle line segment means the many, and 1 to 1 optional, 1 to 1 optional, and that means this side is existent, but this one is optional, and then 1 to many optional, and then again this one is used, because depending on the kind of, this is a Martin information engineering, that's not necessarily worry, and then depending on the modeling language you use or select, the model final picture may look different, and they are modeling the same thing. And this is an alternative notation. If it is a 1 to many, we use a number. This is the commonly used one. If the two entities associated with 1 to many, both the sides we put 1 and 1. If it is 1 to many, the one side put 1, other side what we usually put is uppercase character. And then not only that, in there optional is not shown. It seems to be everything is mandatory. But anyway, but the what thing is, this one says alternative one, cardinality is explained not by using that the oval-like thing with the letters. If it is a 1, number 1 or the character 1 is used. If it is many, uppercase character is used. Whatever the uppercase character used could be any uppercase character. And then that one you can see is 1 1 1 1 1 to n 1 1 0 01. Likewise, different notations are used. And then the using relationship to define access path, and this is what we say. Then the employee has association with department because employee work for department, one department many employees work, and then employees work on multiple projects. One project there may be multiple employees, and the department may control projects, and then for that purpose project should access. That is a part of the ERD diagram you saw earlier. And by using that, there is a possibility of finding, and then the employee, we can find, for example, department, we can find who are the employees work for this particular department. And similarly, for a project, who are the employees working for this project. Plus, when we get a particular employee, we can find this employee is working for which projects like thing. That is the access path what we talk about. And then the detailed conceptual modeling, and that is where we have to talk about then how to add the additional component, like earlier I mentioned. Earlier diagrams, what we talk about is entities, relationships, existence, mandatory, cardinality, and all those things are we discuss. But none of those entities we saw earlier, they are not fully described. They are not fully described. In order to describe them fully, what we need is we have to specify the associative attributes also. Associative attributes. And then basically there are different type of attributes we consider, and the first one is in general, what we call an attribute is a characteristic of entity, and then it is represented by a labeled oval. And then the attribute can be in 3 types. simple, multivalued, and composite. What is the simple attribute mean? And then if there is an attribute which cannot be broken into pieces, if an attribute it cannot be broken into pieces, for example, just say age. Age cannot be broken into pieces, right? And then, but if you consider a name, name can be broken into pieces like first name, middle name, and so on. But the what you call age, like age, identity number, those things cannot be broken. Those kind of things are known as simple attributes. And multi-value attribute means when there is an associative attribute per an entity, but that can take multiple values. That can take multiple values. For example, name. Even our ID card, there are two entries for name and the other name. One person may have multiple names. And similarly, one person may have multiple phone numbers, multiple email addresses. And therefore, they can be viewed as multi-value attributes. Another one is a skill. One person may have multiple skills. But when we model the database, conceptual modeling is concerned, the whether a particular attribute identified and it seems to be multi-value, we do not always model this with doubly lines over. Because the reason is, in the database application, in the database requirement, if we want to have all those multiple values of that particular attribute, then only we model it as a multi-value attribute. For example, even a particular person has multiple emails and the multiple phone numbers. If the database requirement is to have at least one, just say one email address or one phone number, and then though it seems to be multi-value, we can model it as simple because what we need is one email or one phone number for contact purposes. But the requirement says to store all the available contact details, and then you have to model email as a multi-value, phone number as a multi-value, because that is a requirement of the application. And then composite attribute is the attribute which can be composed into parts. Name, as I mentioned, first name, middle name, last name. Address, street, city, state, province, and country, and so on. And then those are composite attributes when we identify. But once again, whether we model them as composite or simple is again depend on the application requirements. Then even the address can be broken, name can be broken into parts. If the system does not have a requirements to access address by the country, address by the state, address by the city, address by the street, and so on, then no need to model it as a composite. We can model it as a simple attribute and put everything, all parts together. Name is also the same. If the system says that we want to access the employees by their last name, then we have to model it as a composite attribute because then we are going to access the database by this last name. Otherwise, even though a particular attribute seems to be multi-valued or seems to be composite, we don't need to model them as multi-value and composite always. The modeler or database designer has to decide based on the functional requirements whether that attribute to be modeled as multi-value or composite. And then we also have stored attributes and then the derived attributes. Stored attributes are the attributes we are going to store on the database. Once we identify the attributes and model it, and then if we want to store a value for that particular attribute, that is called stored attribute. But sometimes there are attributes, they are not really stored in the database, but from the stored attributes, we can derive attributes. And those are known as derived attributes. For example, if the stored attribute is date of birth, if we store the date of birth as an attribute associated with a particular entity, but when we retrieve the data, we don't want to retrieve the database, date of birth, but what we really need is the age. And in that case, we say that age is derived attribute because age is not stored, but age is derived from the stored date of birth. And then the identifier attribute, that is what we call unique attribute. And then if there is a unique attribute for a particular entity, and those unique attributes are indicated with the underline, or in other words, just putting an underline in the label of that particular oval. And then the uniqueness means within the database, for a one given unique attribute value, there can be at most one entry in the database. For example, if the employee number is unique, given a particular employee number, you can find only one employee within the database with that particular number, not more than one. And then the composite identifier, if there are multiple composite values, and then here in the flight ID is the identity, but it is a composite attribute, and in that case that identity is indicated by underlining the composite attribute, but parts are not underlined. Parts are not underlined. Okay, in generally most of the cases, not always, for the identifier attribute is a simple attribute, but there are some cases like earlier that flight thing, there might be a composite identifier. But we hardly use multi-value attribute as identifier. And then the details conceptual design, here you can see entity is department, identity attribute is department number, the department name is there, the location is a multi-valued attribute, and then the phone is simple, employees is simple. But this employees is derived. Employees is derived, that is not stored, that is derived one. And then here department number, this description, unique identifier, name of the department, that is also unique, location of the department, multi-value, phone number of department, it is simple, an employee, number of employees in the department, and this one is a number, not the employee name of that mean, that can be derived from the access part. And then here what the important thing to notice is here you can see that every identifier attribute should be unique. For a one entity, there might be multiple unique attributes, but you should underline only the identifier attributes. Because even the department name is unique, you should not underline this one. If you underline it, then what that indicates is the department number and the department name together define the uniqueness for department. And therefore, whatever the attribute you use for unique identification of instances should be underlined, others should leave as normal. This is another one for a project. And this is another employee, then it says everything, right? This employee name is the composite one, and then it is parts are also described. And here you can see that even address seems to be multi-value, sorry, composite. It is not designed as a composite one. It is designed as a simple attribute. Employee number, name, national ID, address, salary, all those. And then the relationships, works for department, supervise employees. And the first part indicate it is attributes, and the next two indicate their, employee relationship or association with other entities of that one. Here, that's it. Employee, that the employee one, you can see only employee number is composite, employee number is unique, but there are no multi-value attributes. Even the employee could have multiple address, only one address is stored in the database. And this is the dependent, And then here in particular thing is the dependent, it is the dependent name is part of the key. So that means it is not the entire thing, but we discuss it later. And then the department name is unique for the dependent, but it may not be unique for the database. We talk about those things in detail later. And this is the one of the completed ER diagram, and that is there are four entities: employee, department, dependent, project, with their attributes. Okay, now it's now next what we talk about is now we talk about the ER model language symbols, and then we talk about how to represent the entities, association, and the attributes. And then even these entities, we already show that there are three types of attributes: simple, composite, and multivalued. And similarly, entities also have two types. One is the regular or strong entity, other one is the weak entity. The strong entity means if any entity having at least one unique attribute, any entity having at least one unique attribute is known as employee. And then in that way, if the weak entity, the definition of the weak entity is not something like entity does not have unique entity. That is wrong. That is not the definition. Weak entity means an entity which cannot exist without the existence of and existence of a strong entity. To weak entity that can exist only if there is another strong entity. For example, dependent. There cannot be a dependent without employee, because dependents means the employees associatives. And then without employee, there is no dependent. And then you can see that how we differentiate these two in the model. And then strong entity is a single line rectangle, whereas weak entity is double line rectangle. And then the identifying the owner. And then for that one is usually employee is the owner of the dependents. To show it, what we can do is, and then we can show that relationship also as weak by using the double line diamond. That is how we indicate the, and here you can see now, in the previous diagram, it was not clearly shown. Here you can see that employee has dependent, but there is no differentiation between the employee and the dependent. That means the dependent and owner. But now it has. Employee has dependents. But this is both dependent and the relationship, or entity and the relationship are marked with double line, oval and the entity. This slide shows the sample definition of the entity. Department, it is a regular, and this dependent, it is weak, then we just documentation. And then here again, each attribute, domain, component, those things are described. And then the relationship, definition of the relationship, workflow, it is a binary one-to-many, associate each employee with the department, constraint, each employee must be attached to a department, no attributes, and so on. Then the domain constraint, the specific sample domain constraint, employee identities, and then it should be a character type, length should be 5, allowable characters is only digits, and that kind of thing. These are the domain constraints. This is how you should specify the date. Data type is date, 2-digit date, 2-digit month, and 4-digit year, and so on. Those are the constraints applicable. Okay, now we will continue from here onwards next week. This is the associative entities. Do you have any questions to ask regarding what we discussed? If you have any questions, now you can ask. Okay, if there are no questions, I stop the lecture and I will upload the video, and then the next